Let me check on the homeworks first. Homework 2, I think most of you have already submitted that, I think, from the count of numbers of those who have submitted. I think most of you have submitted, or all of you. For the project, some of you have asked me for an extension. I'll give you till the end of the week, but you need to submit because of the time, because we need to do other things with the project. So by the end of this week, by Friday, I'll extend the deadline so that you can submit the design, so that I can have a look at it and then give you my opinion, so that you can start making the model using Lagrange formulation. So you need to do some very clear sketch, or if you can do it with AutoCAD or a program like Visio drawing or something of that sort, would be better. So basically, you need to draw the beam, the ball, and then you tell me what sort of sensors you need, what sort of actuators, and what are the dimensions, the numbers for the different parts of the system, so that you can start modeling based on that. So I can tell you whether this is okay, acceptable or not, or you need to modify something, and accordingly you'll start modeling, inshallah. Any questions regarding that, the project? If you have any questions? If no questions, then I'll, as I told you, I'll put the deadline as of Friday. I mean, it will be Friday. I don't remember the date exactly, but it will be Friday of this week. And what you call the things that you need to submit is the sketch, the schematic diagram with some description. So try to make it as clear as possible so that I can give you a feedback which is useful for you. So make it as clear as you can make it, so that the feedback that you will get will be useful for you. Homework 3, I'll upload it also shortly, I mean within the next few days, inshallah, together with the solution of homework 1 and 2. As far as the course is concerned, we are still at this point here where we're trying to understand the system by analyzing this. We are done with the stability. Now we are trying during this week and the week, the coming week also, to look at how the poles, the solution of the characteristic equation, will change when you change a particular parameter. Because as we said, the poles are very important. They determine the behavior of the system and the stability of the system. So we want to see if I change a particular, what you call parameter, which is usually the gain of the controller, what will happen to the poles of the system. Later on, when we start doing design, this understanding here will help us in the design. We'll be able to design based on our understanding of how the poles will change when we change a particular parameter. A closed loop feedback control system is like this. So you have the feed forward or forward transfer function. Usually this is the usual, you can say, a block diagram of a feedback control system. And you will have the output, and the output is fed to some sort of a transfer function. It could be just a filter, or it could be another controller which is put here. And this will be compared with the input, and the actuating signal will come from there. Usually we have a controller somewhere here. We'll have another block here for the controller. But for the analysis that we want to do now, we can combine these two as one block, and we'll just call it J of S, the forward transfer function. So we have the KGSH of S, which we call it open loop transfer function. We call this open loop transfer function. And then the KGS, the forward transfer function, which is this one, the forward transfer function. And then the feedback transfer function is this transfer function, or this block that we have here. So those are just terminologies that we need to get used to so that we can use it appropriately in the right way. So KGS H of S is the open loop transfer function. KGS is the forward transfer function, and h of s is the backward transfer function. And then k is the gain that we will change. This k here is the gain that we will change, and usually it is positive. And we'll see how the poles of the closed loop transfer function will change. This is the closed loop transfer function now. If you want to replace all of this block diagram here with just a single block, then you replace it in this way. So this one is the forward, again, transfer function. H of S is the feedback transfer function. This is the feedback transfer function. And then these two together, the multiplication of these two, we call it the open loop transfer function. And the closed loop transfer function is the whole transfer function that will result from simplifying this block diagram. Now, we have seen before that the response of a given system is related to the location of the system poles. The poles are the solution of the characteristic equation. The characteristic equation is the equation that represents the denominator of the closed loop transfer function. So the solution of 1 plus k g of s h of s equals 0. This is the characteristic equation. The solution of this, we call it the poles of the closed loop transfer function. The poles of the closed loop transfer function. So we've seen that those poles, the solution of the denominator of this equation, d of s equal to 0, will determine the response of the system. So the solution will be a complex number, and this complex number, depending on its nature, whether it's real root, if it is a real root, then you will get a response which is like this: a constant, e to the minus sigma t, where sigma is the solution of the characteristic equation, if it is a real number. And if this is made up of a complex number, I mean the solution, if it is a complex number, then you will have complex conjugate roots, and the solution will be sinusoidal. You'll have some sort of oscillation. The amplitude is related to the real part of the complex number, and the frequency is related to the imaginary part of the complex number. So the position, again, of the pole is very important. That's what we've learned before in the course. Important for stability and important for the transient response of the system. So depending on the nature of that poles or those poles, you may have real poles or real roots, and in that case, the system will be overdamped, and you'll have a solution which is like this without any oscillations. And if you have only imaginary part, then you will have an oscillation which is not decaying with the same amplitude. And if you have a complex number, which is made up of real part and imaginary part, then you will have a stimulation, a response, which is similar to this. We call it an underdamped response, where you'll have a damped oscillation, an oscillation with an amplitude that is decaying with time till it is constant. So now when we have a closed loop transfer function block diagram like this one, we have the feed forward transfer function, we have a gain, and we have the feedback transfer function, and then the whole thing will make up a sort of a block which is represented by this function, transfer function. Then the poles, which are the roots of the characteristic equation, this one, will be changing depending on the value of k. If we have a gain which is changing. So if you have a gain here which is changing, the solution of this equation will change for sure, depending on the value of that gain k. So the objective of this part of the course is to see how the solution S that you'll get from solving this equation will change its what you call its value depending on the value of the gain k. So you want to change k and see how this S will change, because later on we'll be designing that. We'll be choosing where to put this S by choosing k. But now we want to just analyze. So now we want to just analyze what will happen. What will happen if I change k from k equals 0 to k equals infinity? what will happen to the position of S? Where will S be, the solution of this equation? So that's the objective of this 2 weeks of this part of the course. And then later on, we will have a certain desired S because of a certain desired response that we want. We want a certain percentage overshoot. We want a certain time to the first pick. We want a certain, what you call steady state error, or something of that sort. How we'll choose K, how we'll choose first where to put S, and then how we'll choose K. So that's for design. But now we'll just look at K as we change it from 0 to infinity, how this will change the position of S. So that's the objective of the course now. So the poles of the closed loop transfer function will be affected by the change in K. And let us represent the transfer functions in terms of the numerator and denominator of the polynomials. So if this is my g of s, the numerator is ng of s, and the denominator is dg of s. And then if this is my h of s, the feedback transfer function, and my numerator is nh, and denominator is dh, then the closed loop transfer function is this, which I can represent in this way. So I can write it as equals to k. G is n g over dg, the denominator, divided by 1 plus k, and then I have g again, so ng divided by dg times nh, which is the representing h of s, nh, the numerator of h of s, over the denominator of h, the denominator d of h. Sorry for that, the pen is not writing properly. The denominator of h. Now I'll just simplify this by having this as my common denominator. So I'll have here d, g, dh divided by dg, dh plus k, ng, nh. And the numerator will be the same, kng over dg. Now this dg will go with this dg here, okay, and then I will simplify this, so I can write it as k ng ng, and this dh, I can take it upstairs, so that will be dh here, divided by dg dh plus k ng nh, which is what we have here as a result of that simplification. We want to write it in that way because shortly that will give us some insight into how the behavior of this solution will be if you change k. So this is the closed loop transfer function now in terms of the numerator and denominator of h of s and g of s. So far I think we are okay. This is just another way of writing this equation, but in terms of the numerator and the denominator of g of s and h of s. So the conclusion is that the closed loop transfer function in terms of the numerator and the denominator of g of s and h of s could be written in this way. Now the zeros of t of s, the zero is what makes this zero, will be what? In that case, it will be the zeros of g of s, because this is g of s. G of s is n g over d g. So what makes this zero, which is what makes this zero, is what will make also t of s zero in that case, because if this is zero, t of s will be zero. And the same for the other term here, which is the denominator. Fadal? Is it okay? So far it's fine?
Yes, good.
Yes. So t of s will be zero if ng is zero, which means the zeros of t of s are the zeros of g of s, because what makes g of s zero is ng. or the poles of h of s, because what makes t of s also 0 is the denominator of h of s, the denominator d. So the poles of h of s. So that is the zeros of t of s. But we are not interested in the zeros. We're interested in the poles of t of s. The poles of t of s are a function of k. So it's more complicated. I cannot relate it directly to the g of s and h of s, because this function here is a function of k also. It changes as I change k. So it's more complicated than the zeros. The zeros are easy to determine, the zeros of t of s, but not the poles. The poles of t of s, what makes the denominator 0 is a function of k in that case. So it's more complicated. I need to solve that equation. As an example, if I have g of s as such and h of s as this, then the closed loop transfer function, when I sort of plug in the numerators and denominators, will be something like this. So you can see that the zeros are easy. The zeros of g of s and the denominator, the poles of h of s, will make t of s 0. But the denominator is more complicated. I need to solve this equation. S cubed plus 6 plus ks squared plus 6 plus ks plus 3k. So I need to solve this for different values of k in order to find the poles, to find the solution for this equation. It's more complicated. And we know that transient response is closely related to the location of these closed loop poles. So we need to know them, because our transient response is related to the position of the poles. The location of the closed loop poles depends on the value of the loop gain chosen. Loop gain is k. The loop gain chosen, k plus also the controller that I may have. But in this case, it is just the k, the value of k. It is important to know how the closed loop poles move in the S-plane. So we want to do that. We want to know how these poles will move in the S-plane as we change k. And it's the gain that we adjust, but also the compensator later on. The compensator is the controller. Compensator is the controller. So if we combine these two, the gain k and the controller, it will give me the desired results. It will put my poles in the right place if I choose k properly or choose the compensator. At this stage, we'll not worry about the compensator. That's later when we design controllers. For now, we'll just look at the gain. When I change the gain, what happened to the result? What will happen to the poles? What is the solution of the characteristic equation? As an example, let's take this example. Let's say that I have kgs is like this. I don't have h. Let's say h of s is 1. So I have this as my feed forward transfer function. The closed loop transfer function will be this one. This one is my closed loop transfer function, which is, if I am to write it, it is the, we don't have to do it in details, but my closed loop transfer function T of S or F of S equals to kg over 1 plus kgh, but h is 1. So if I try to plug this here and here, I will get this equation as my f of s. So this will be my f of s if I do it. Now the solution of this one, equals to 0. Equals to 0. This solution, if you try to do it, you will get this as your expression for S1 and S2. We can do it very quickly just to convince you that that's the solution. It is minus b minus this one, minus k minus 2 plus or minus b squared. B squared is k plus 2 squared. So that will be k squared plus 4 plus 4k. So this is b squared minus 4ac. 4acc is k, so minus 4k. Over 2a, a is 1, so over 2. So if you simplify it, this will be minus k plus 2, k plus 2 divided by 2, plus or minus 4k will go with 4k. And then if I take this 4 here outside, then it will go with 2. So I'll be left with k squared over 4 plus 1, which is what we have here, which is this expression there. So you can see that that's the solution. Now what I want to do is to draw this S1 and S2 in the S-plane, where you have the real part and imaginary part. Okay. Now let's see, as k changes from 0 to infinity, what happens. So let me just erase all of this. We don't need it. When k equal to 0, what is S1? When k is 0, this is 0, and this is 0. So what will be S1 in that case?
-1.
-1. And then this is 0, but you have -1 here, and then you have something here also.
Oh,
so -1,
0.
plus 1.
Plus 1.
Plus 1. So 0. So that's S1. What about S2? This is 0 again, and this is 0. So it will be -1, -1, which is -2. So you have one solution here at 0, here, okay, where you have the pole. So you have the pole as 0 because one of the poles is 0, and then you have another pole at -2. So you'll start here and you'll start here at k equals 0. What about k equals infinity? When you have k equals infinity, when k tends to infinity, that's a bit tricky, but you can get it also. You will have what from here? You will have S1 equals -2 -2 over -2, that's -1, and then plus k, which is infinity, over 2, so that's infinity. Okay, plus here you have infinity squared over 4 plus 1, which is infinity squared, and then you have the square root of infinity squared, so that will be infinity. Asif, infinity. So it will be like this: -1 plus infinity, no, -1 minus infinity because of the minus here. So -1 minus infinity plus infinity, what is that?
0.
0. You have a very large number, and minus a very large number, and then you have -1. It will not affect it. So this is 0. So is it 0? No, it's not 0. It's -1. -1. It will be. It will be -1. You have a large number here, minus a large number, which is divided also by, because this one k squared over 4 plus 1 is just k squared over 4, which is k over 2, and here k over 2. So it will cancel out and you'll have -1. And then what about S2? You have -1 plus k, let me put it as k first, but k is tending to infinity, minus, here you have very large number squared over 4 plus 1. So this will be just k squared, a large number squared, so it will be just k over 2 in that case. Just like this one is also over 2. This is k over 2, and here minus k over 2. Is it minus? And this is minus. Asif, minus here. Atfadal?
Nothing. Just I want to say that was minus instead of plus.
Yes. Thank you. So that minus there. So minus, minus. So now what will that be? If k is tending to infinity, it will be infinity, minus infinity. Minus infinity. Okay. So it will start from 0 and -2, and then it will end at one of them, where S1 will end at -1, and the other one will end at infinity. So this one here will start from 0, and then it will go to and end at this number, which is -1. So it will go from here to here, one of them. And this other one, it will go to infinity, from here to infinity. This -2. this one here, minus 2, it will go to infinity, to minus infinity. So it will start from minus 2, it will remain as real number. It will not be a complex number. And this one the same, it will not be a complex number. It will not be a complex number. It will be just a real number starting from this number, and it will end at minus 1, which is this one here. So it will start from one of the zeros, which is one of the poles, which is s equals 0, and it will end at the 0, which is minus 1. And the other one will start at minus 2 and end at infinity, this one here. It will start from minus 2 and end at infinity. So this is now a drawing of the, because this is simple. Here we can see the solution, we can draw it very easily. But sometimes it might be very difficult to do it in that way by evaluating the solution of S1 and S2. So we'll need to find ways of sketching the solution in a simple way, in a very simple way by following certain principles. That's what we want to learn. What are those principles that will enable me to solve the solution, to get the solution or to sketch the solution as I change K without evaluating the function for every K, without solving for every K. So this will be the solution in that case for this one. It will start when K equals 0, it will start at the pole, which is 0, one of the poles, which is 0, and minus 2. And then this one will go to the minus 1. Sorry, it will go to the minus 1, which is the 0 of the open loop transfer function. And the other one will start from minus 2, which is one of the poles. And then it will go to infinity as K changes to infinity. So this is now the root, we call it the root locus. Root locus. Root, sorry, here, root locus. The sketch, the diagram that shows the value of S as I change K. We call it the root locus. And that's what we want to know, how to draw it, how to sketch it for different transfer functions for different values of K. Starting from what we just saw now, the starting points are the finite poles of GS H of S. You start from the poles, you start from 0 and minus 2, from 0 and minus 2. So that's one principle. You start from the poles of the transfer function, open loop transfer function, and you end at the finite zeros of the transfer function. So you end at the zeros of your transfer function, which is minus 1 here. You end at that one, okay? And the infinite, that will learn later, but the infinite zeros also of your open loop transfer function. And so those are the starting point and ending point. Why is that? This is the closed loop transfer function that we have. This is the closed loop transfer function, okay? Which we can write it using the numerator and the denominator of G of S and H of S in this way. In this way. Now, when K equals 0, what happens to this one? When K equals 0, tends to 0, when this is very small. So this can be 0 nearly. Or not? When K is very small, this will be nearly 0. So this will cancel out. Not cancel out. This will be a very small number. And my denominator will be made up of this. Will be made up of that one. The denominator of G and the denominator of H. So the poles of G of S, H of S will be the this one. The poles of the GS H of S, the closed loop transfer function. The poles of this one will be the poles of the open loop transfer function. What will make this 0, okay, is what makes this one, the denominator of this one 0. Let me repeat this. Maybe I didn't say it clearly. Let me repeat it again. This is the closed loop transfer function, okay, which I can write it using numerator of G and numerator of H and denominator of H and denominator of G in this way. So this is my closed loop transfer function now in terms of the denominator and numerator. My characteristic equation is this one equal to 0. This one here equal to 0, or this one equal to 0. This is my characteristic equation that will enable me to find S that makes this 0. And we said this is important because the position of S that makes this 0 here is very important in determining the solution, the response of the system. Now what happens when K tends to 0? When K tends to 0, this part here will be nearly 0. So this will not appear. Now what makes this one 0? Okay, this one, what makes this 0, or what makes this whole thing 0, is what makes this 0. So the solution of this one is the solution of the characteristic equation. So the solution of this one is the solution of the characteristic equation, which means the denominator of this and this will be the the characteristic equation of the closed loop transfer function. Is it clear, or? Shabab, is it clear, or is not that clear?
Yeah.
At this point?
Doctor, it's clear. But doctor, yeah. You mean just in case when K goes to 0?
Yes, when K equals 0, as we saw here, if you remember in this one here, let me erase this. Maybe from this example, you'll see it very clearly. If you remember when K equals 0, when you put K equals 0 here, this is 0, and we put this 0, okay, and the same here, this is 0 and this is 0. The solution for S1 and S2 was what? When K 0, this was minus 1 plus 1. So this was 0. K equals 0. S1 was 0, if you remember. And S2 was minus 1 minus 1. Okay, so that was S2 equals to minus 2. Now 0 and minus 2 are this ones. The denominator, what makes the denominator of the open loop transfer function 0. So what makes this 0 is what makes this 0, the closed loop transfer function, f of s. So when K equals 0, the poles of the open loop transfer function, which we know, this is 0 and minus 2, are the solution of the closed loop transfer function. So your root locus will start at these two poles, 0 and minus 2 when K equals 0. So that's what this says also here. This one here, it says the same thing. So this is just to prove it, that what makes this 0 is what makes this 0. So the poles of the closed loop transfer function are the poles of the open loop transfer function when K equals 0. So that's one thing. When K tends to infinity, if K is infinite, it's very large. What happens? When K is very large, then this part compared to this part is very small. So I can remove this part. This part I can remove it because this one is very small compared to this because K is very large. Now I will take K as a common factor. Take K as a common factor. Okay. So if you take K as a common factor here, what will happen here? I mean, one way of looking at it, either you remove this, the whole thing here, this one is removed, and therefore now K will go with K. And now what makes the whole thing here is 0 is the numerator of this one and the numerator of this one. Not the denominator. Here it was the denominator. But now here what makes the denominator of this one, the denominator of this one, 0 is the numerator of G and H, the numerator of this one, not the denominator, when K is infinite. So what does it mean? It means your poles will end up being at the zeros, the poles of the closed loop transfer function, the closed loop, the poles, what makes the denominator 0, what makes this denominator 0 will be what makes the numerator of this one 0. As you can see here, the numerator. So let me just say it again. Yeah, will be better to repeat this. Forget about this one. This is another way of saying it. Forget about this one. Okay. Now, when k is infinite, when k is very large, this part is very large compared to this part. So therefore, I can remove this part because k is very large. Okay. Now, since I removed this, I can now cancel out this k and this k, which is not that important. What is important is that what makes the denominator now, what makes this one 0, because I want to find what makes this 0. Now, what makes this 0 is what makes this 0, n g times nh. And this is the numerator of the open loop class transfer function of this one, k gs h of s. The numerator meaning the zeros of your open loop transfer function. Going back again to this one, to this system here, again, okay. When k is infinite, when I put k here as infinity, what happened? Your poles, the solution of this one, will be -1 and infinity. When you put k as infinite, when you put k infinity, the solution of this one will be either -1, the 0 of this one, not the poles, not this, the 0, the numerator of k g of s, okay, -1 and infinity, because I have only one 0 here. I have only one 0, which is -1. So one of them, which is this pole, will start from the pole of the open loop transfer function, okay, and it will end at the 0 of the open loop transfer function, which is -1. It will start at 0 of the the pole and end at the 0 of the open loop transfer function, which is -1. The other one will start at -2, the solution of this one -2, but then it will end at infinity. Okay, why is that? Again, we'll see it here. Okay. So it will end at the zeros or at infinity. Maybe not in that one. Well, I'll prove it later. Not now. Why it will end at infinity? Not because we don't have another finite 0. We have only one finite 0, which is -1 in that case. Let me just go back to here. So this is one principle. We'll prove it next time again. So don't worry if it is not that clear at this moment. But I just want to show you. عرفتوا كيف وش يسمى ترسموا function إذا كان معك f of x equals, let's say, x squared plus 1, or a very complicated function. You usually how you draw a function. If you have a function, let's say صاد تساوي دالة معينة as a function of x or sin. كيف ترسمها؟ كيف ترسم f of x? Can someone tell me? Let me stop sharing, and then I'll if I can have one of you telling me how you draw a function f of x. Thwaini, let's say you have a function f of x and you want to draw that function. How do you do it usually? Thwaini?
نعوض.
Oh, Muhannad, yes. One of you? Yes, Thwaini. Yeah. So how do you draw a function if you have f of x? How do you draw it? Just in simple terms. How do you draw it? No, how you draw it? Yani, what sort of you will do in it to be able to sketch it?
X, Y, or what? You mean? I don't.
Yeah, y as a function of x. I'll put a particular function here now. Just a minute. Let me just put a particular function, and then you'll tell me how you will do it. So let me just put a particular function here. Let's say I have f of x equals to, let's say, x squared times sine of x. How will you draw this function? You want now to draw it. You want to draw x versus f of x. How will you do it?
نعوض بالأرقام.
أحد الطرق إنك تعوض بالأرقام. تقول مثلا الإكس قيمتها كذا.
Choose a value.
F of x. We'll choose values. You put 0, you put 1, you put 2, you put 3, you put 4, and so on. But this is a very complicated function. It's not a straight line. This is x squared times sine of x. So if you do it this way, you need either a computer to do it, or you need to really do a lot of calculations in order to find the shape of this function. Do you have another way of doing it?
Find zeros first.
Put x equals 0, put x equals 0, and find f of x. That's one. The other one, you are saying find what makes f of x 0. Find x that makes f of x 0, or not? That's what you are saying?
Yes.
Yes. So that's one way. What else? What do you need also?
What makes the derivative 0?
What makes the derivative 0? Okay, so that's another thing. So you'll find d of f of x, d of f of x by dx, and you'll equate this to 0. Okay, so that's one thing. So 1, 2. Okay, what else? You may need to do something else.
Exclude values that may make the denominator 0.
So exclude the values that makes your function f of x not defined. So there are points where x, when you put x, your f of x will not be defined. Okay, so that's another thing. What else? You need also to do something. What happens when x is infinity? So that's also an important thing. What happens when x is infinity? What will happen to f of x? So you may need to know that when x is infinity or minus infinity, what will happen to f of x? So that's what we want also to do with this one. We want to solve this equation here. We want to solve it. We want to solve this equation equal to 0. We want to find s that makes this 0. So to be able to do that, we need to understand how it behaves as you change k. As you change k, how this function will behave. So that's what we want to understand. So today I will just look at that, and then the next lecture, we'll see what are the steps needed to solve it. So now we're trying to understand it. When k equals 0, what happens? When k equals 0, we find out when you put k equal to 0 here, your solution for this one, the solution S, will be the poles of the open loop transfer function that we know, 0 and minus 2, when k equals 0. When k equals infinity, when you put k equals infinity, the solution of this one will be the zeros of your numerator. What makes this 0? So at infinity, you'll be at minus 1, at minus 1, at infinity, when k is infinity. And if you have a less number of zeros than number of poles, because here we have 2 poles and 1 0. So one of them will go to minus 1. The other one will go to infinity. And I will explain next, maybe today or next time, I'll see whether I have a slide here. I'll explain why it goes to infinity. So now we understand when k is 0 and when k is infinity, what will happen to the solution of this one. So this is one principle. Okay, we'll continue. So starting point and ending point, we know now how to get them. So, and this is just a very quick proof of why we are getting it as such. When k is 0, why we're getting it as the poles of the open loop transfer function, and when k is infinity, why we're getting them as the zeros of the open loop transfer function. Okay, so that's one result. Let's take another example. Let's take this example. We have the characteristic equation for this one. When you have, this is my open loop transfer function in this case. The closed loop transfer function is this one, and the solution of my characteristic equation is the solution of this equation polynomial. I have to find s that makes this 0. So this is my characteristic equation. The roots will be as such. Okay. Now, when k is 0, what is the solution? When k is 0, according to this. This is when k is between 0 and 1, and this one is when k is between 1 and infinity. Why is that? Because when k is larger than 1, I will have a complex number here. When k is larger than 1, I'll have 1 minus, let's say, 2. I'll have the square root of minus 1, which will be a complex number. So that's why we are dividing it into k between 0 and 1, and k between 1 and infinity. You'll have a complex number. Now, when k is 0, what will be the solution of this one?
0 and minus 2.
So 0 and minus 2, which is the poles of my open loop transfer function. Okay. Now, when k is infinity, I don't have a 0 here. So when k is infinity, both of these two, which have started from 0 and minus 2, they will end up at infinity, both of them. And actually, the roots are two complex conjugate numbers, minus 1 plus or minus j, the square root of k minus 1. So if you try to solve this and plot it, you'll get this one, this diagram or this graph for your s as you change k. So when k is 0, you'll start at the pole of the what you call open loop transfer function. And then as you increase k, they will move, this pole will move their position till they meet at this point. You'll have two solutions which are the same number, repeated roots. And then you'll start getting two complex conjugate roots. So the solution will be like this. And one principle that you'll get from here, and also next time maybe we can prove it, is symmetry around the real axis. The shape of the root locus here will be the same as the shape of the real root locus there. Can someone tell me why? Why you'll have symmetry around the real axis? Why the shape here, the shape on this part, should be the same as the shape in this part? Why is that the case? Can anyone tell me? Why is that true? Why the shape of the root locus will be symmetrical around the real axis? This is the reason. When you have complex, what you call solution, the complex solution will be happening as two conjugate numbers. One number will be here, another number will be here. One number will be here, another number will be here. So that's why the shape will be symmetrical around the real axis, will be the same. So that's another principle, will help us in drawing the root locus. So the first one is that your roots, the solution of this one, will start from the poles of your open loop transfer function from 0 and minus 2, and will end up at the zeros of your open loop transfer function. If you don't have a 0, then it will end up at infinity. It will end up at infinity. And next time I'll explain why it ends at infinity, or maybe today. It depends on the slide whether we'll reach it or not. So this is the first principle. Second principle, the shape of your root locus will be symmetrical. Whatever happens here will happen here. It will be symmetrical around the real axis. So that's another thing that will help us in sketching the root locus. So we have two principles so far. So the symmetry around the real axis. So this is a principle that we need to put in mind as we draw or sketch the root locus. The other one, the number of branches will be equal to the number of open loop poles. The number of branches, let me go back here. The number of branches, this branch and this branch, will be equal to number of poles that you have. In the here we have 2, so we'll have 2 branches. 2 branches that we'll have either on the real axis, or it will be branches which will travel in the what you call the whole. I mean, the poles will be having complex. Real part and an imaginary part, and therefore it will be not only on the real axis, but also it will be in the entire S-plane. So the number of these branches will be equal to the number of poles of the open loop transfer function, or it will be equal to the order of the polynomial of the characteristic equation. So here it is squared, So we'll have two branches. So we'll have two roots of the characteristic equation, and those two roots either will travel along the real number axis, I mean the real axis, or they will travel in the S-plane, entire S-plane. So it will be a complex conjugate roots. So the number of branches will be equal to the number of the order of the polynomial which is making up the characteristic equation of your system. So this is another thing to keep in mind while we are drawing or sketching the root locus. Symmetry around the real axis and the number of branches equal to the order of the characteristic equation. We may prove it also next time, but now I just want you to know some of those principles that we'll be making use of, some of the properties of the root locus that we'll make use of in sketching the graph. So let's take an example, this one here. If we try to draw it by solving this, not this one actually, by solving this equation equal to 0, if you try to get the solution using a computer, as you change k, you'll start from the solution of this one, from 0, -4, and the solution of this one. You'll start from here, 0 and -4. You'll start from those. As k changes, you're at k0, you'll start from here. And then as you change k, the solution will move from one point to another. They will move as you change k. That green points are the solutions of the closed loop characteristic equation. So it will change as you change k. It will move, and the number of branches will be equal to the number of poles that you have. So we'll have 4 branches in this case, because we have 1, 2, plus 2 poles, and you'll have 4 branches. So here we have 1 branch, this one. This is another branch, and this is another branch here. 4 branches that we'll have for the root locus. Plus, you have symmetry around the real axis. You have symmetry around the real axis, and you will start from the open loop poles, from 0, -4, and the solution of this one, which is this one and this one. You'll start from there, and then you'll move to the zeros of your open loop transfer function. But we don't have any zeros, and since we don't have any zeros, then it will end up at infinity. So all of those 4 will end up at infinity in that case, because we don't have any zeros here. Otherwise, one of them will go to the 0. So those are the principles. And now we have computers to do this sketch for us and to solve the equation. So we don't actually need to solve it. We don't need to solve this one. We can just define our system. The numerator is 1 without the k. The numerator is 1. The denominator is s times s plus 4 plus times s squared plus 4s plus 20. So this is my what you call denominator. And then you just write root locus in MATLAB, and you will get a graph that shows the root locus. So we don't need actually to sketch it now. But people at that time, before this computational power that we have now, they did want to solve and to sketch this root locus. That's in the 50s or 40s or even 60s. It was a must to draw this root locus in order to understand the system and in order to design controllers. But nowadays we don't have to do it, but we need to understand it so that later on we can design controllers. But in order to get this, you don't need actually to know how to sketch it. You can just write this command rlocus in MATLAB, and it will draw it for you. But we need to understand how to do it, because that will enable us later on to move this S from one point to another, to move it from here to here if you want to, by changing K. So unless we understand how it changes with the value of K, we'll not be able to do that, to design the controller. So the idea of learning it is to be able later on to design a controller. So if you issue the command, that program, if I run it in MATLAB, I will get this diagram for the root locus of this particular system. So this diagram here is from MATLAB. So this is just an introduction. After completing this chapter, you'll be able to define what we mean by root locus, which is section 8.1, 8.2 in the book. You'll be able to state the properties of a root locus. I mentioned few of them, but I'll mention more as we go on. And then you'll be able to sketch a root locus. So this is what we'll cover in this week, in today's lecture and Wednesday lecture. How to sketch this Wednesday, we'll know. Today we'll just define what we mean by root locus and state some properties of the root locus that will enable us later on to sketch on Wednesday to sketch the root locus. And then next week we'll sort of learn more about the root locus and use it also to design a certain parameter in order to meet certain transient response specification. So that will be next week or the week after. But for this week, we'll define what do we mean by root locus, what are the properties of a root locus, and then on Wednesday, we'll learn how to sketch a root locus. So that will be the objective of these two lectures. Now, let's say we have this example. So we have g of s, this one here, as s plus 1 over s plus 2. And then we have h of s, the feedback transfer function, as s plus 3 over s plus 4. The open loop transfer function kgs h of s will be this, by just plugging in g of s and h of s. And the closed loop transfer function will be this one, kg of s over 1 plus kg of s h of s. So if you write it, you'll get this closed loop transfer function. The poles of the open loop transfer function are easy to find. The poles of the open loop transfer function, -4, -2, and 0. But the closed loop poles, which are this one, the solution of this one, are not that easy to find. You need to solve this equation in order to find s that makes this 0 for different values of k. So it's not that easy to do it. MATLAB again and CLab will be able to solve this equation and find s for any value of k, and therefore it can plot or sketch the graph of which we call the root locus. But for us, we'll learn how to sketch it, how to be able to sketch it for different values of k. So we need to define or look at some of the principles that you can use, some of the properties of the root locus, and then in the next lecture, we'll know what are the drawing steps, how we'll do it, and then we'll see some examples in the next lecture. But today we'll just learn a few things that will enable us to do it. So let's start slowly. Let's say we have this configuration. The closed loop transfer function is this one here. We know now how to get it. I can write it as the ratio of two polynomials, the numerator and the denominator. I mean, for whatever g of s and h of s that I can get, I can write it as a ratio of two polynomials. This, I can write it also in a different way by putting it as a multiplication of s plus the different zeros that I will have, which are the solution of this polynomial. So I can write it in this way, s plus z1 times s plus z2 times s plus z3, and so on. So this I can write it using this pi notation. So this pi notation, it means I'm multiplying these terms as I'm changing I from 1 to m. So this is like the summation, sigma for summation, but this is for multiplication, the pi. So just another way of writing it, a polynomial which is made up of terms which are multiplied by one another in that way. Okay, so I think you understand it. Maybe you are seeing it for the first time in this course or not, this pi. Did you see it before in any course?
Yes, we have seen it.
Okay, good. So that's the another way of saying that I'm multiplying these terms by one another. The denominator in the same way, it will be s plus p1 times s plus p2 times s plus p3 and so on. So I can write it also using this pi notation. So therefore, this one, I can write it as k, a constant. And then the numerator, I can write it using this pi notation, and the denominator using this pi notation again. We know this gs h of s as the open loop transfer function. I keep on repeating this because it's important to to keep those terminologies in mind as we speak. So GS H of S is open loop transfer function. Closed loop transfer function is this one. PIs or PJs are the poles of the open loop transfer function. These ones are the poles of the open loop transfer function. The poles of the closed loop transfer function are the solution of this equation. So you need to differentiate between the two. The zeros of the open loop transfer function and the poles of the open loop transfer function and the poles of the closed loop transfer function, which is the denominator of the closed loop transfer function, the solution of 1 plus G S H of S times K equals 0. The solution of this are the poles of the closed loop transfer function. So the solution of this equation, if H of S equals 1 for unity feedback, are the poles of the closed loop transfer function. So, and this roots, whatever makes this 0, will change as I change K. As I change K, this solution will change, the solution of that one. So they will vary as I change K. And the objective is to find or to draw the position of this S as I'm changing K. That will be the objective. Now, to be able to do that, maybe this will help representing this complex number as a vector. So S, I can represent S as a vector that comes from the 0 to the position of S. Okay. And Zi, I can represent it, or minus Zi, I can represent it also as a vector. So S plus Zi will be the vector coming from here to here. This will be my S plus Zi. S my Z plus Zi will be this vector. Okay, it will be this vector plus this vector, which will be this vector here that comes from the tail of the first vector, which is this. This is plus Zi will be in this direction. This is plus Zi from here to here, and then plus S, this one, or plus S. So S plus Zi will be from the tail of the first vector to the head of the second vector of this vector. So that will be S plus Zi. Okay, and I can represent it as a magnitude and an angle using complex. This is a complex number or a complex function, so I can represent it as magnitude and the exponential of j theta. So this is just another way of representing a complex number. You can represent it as magnitude and an angle. We call it the phase and the magnitude of the number, which is the magnitude and direction. Another way of saying it. So for the first one will be m1 ej theta z1. Second one will be mz2 ej theta z2, and the same for the denominator. We can represent it in the same way, magnitude and direction. Now the overall function, the result f of s, which is made up of this functions, will be equal to the magnitude multiplied for the numerator divided by the amplitude of the denominator multiplied by one another. And then for the angles, I'll add them up for the zeros and subtract the sum of the angles due to the poles, due to this different numbers that I have here. So this is just another way of representing the function f of s using what you call vector representation or formation or vector notation. So I can represent it in that way. It will be useful later on as we draw the solution of the characteristic equation. So I can represent this function as an amplitude and a direction. So m is the number of zeros that I have, and n is the number of poles that I have, and zi are the zeros of f of s, and pj are the poles of f of s. So in polar form, we can write it that way. So the length of the different amplitude, I'll multiply them by one another for the zeros, and I'll do the same for the poles, and then I'll divide the two by one another. to get the amplitude of the overall function. And I'll do the same for the angles, for the direction. The zero angles minus the pole angles will give me the overall angle of f of s. So just another notation to introduce. This means the angle or the direction of this vector, and this is the direction of this vectors. And the convention for the angle, clockwise is positive, sorry, counterclockwise is positive, and clockwise is negative. I mean, for drawing this, what you call root locus. So counterclockwise is positive, and clockwise is negative. Let's take an example. Let's find f of s when s is minus 3 plus 4j. So what I will do, I'll take this s and substitute here. Okay, and then evaluate the function f of s. Get the magnitude and direction of f of s. So that will be the objective. So what I will do, I'll just take that s and put it there. So we have the poles at 0, 0, and minus 2, and zeros at minus 1. So we have two poles at 0 and minus 2, and 1 0 at minus 1. So for any point s, we'll have it this way, and we'll have this vectors. So this is s, this is s plus 1, this is s plus 2, this vector here, s plus 2. Okay. Now, we have 0 at, I mean, if we take now the this one here, if we take this one s plus 1, okay, and have this point substituted into that expression, so s plus 1 will be minus 3 plus 4j plus 1, this plus 1 here. The amplitude of this one will be what? Minus 3 plus 1 is minus 2. So this will be minus 2 plus 4j. This will be the resulting, what you call vector, when I add 1 to this vector. When I add 1 to this vector here. S plus 1 will be minus 2 plus 4j when s is minus 3 plus 4j. So what is the amplitude? It will be 2 squared plus 4 squared, the amplitude of that vector. 2 squared plus 4 squared, so 4 plus 16, the square root of 20. So this will be the amplitude of the what you call of the 0, I mean of this expression, s plus 1, the amplitude when s equals to minus 3 plus 4j. So this will be the amplitude. What about the direction of this vector? Minus 2 plus 4j. What will be the direction of this vector? S plus 1. What will be the direction of that one? How can I get it? This vector here. S plus 1 minus 2 plus 4j. What will be the direction? This angle from here to here. How can I get it? Tan inverse of what will it be?
4 over 2.
4 over 2. So tan inverse 4 over 2, it will give me this angle. This angle here, this one here. This angle will be tan inverse 4 over 2 from minus 3 to this one here. This distance is 2. From minus 3 to minus 1. Minus 3 plus 1, which is minus 2. This angle is this distance, minus 2. I mean, this one is 2. So the tan inverse of 4 over 2 will give me this angle. And this one, the one that I want to measure it from here to here, is 180 minus that angle. So I can get that angle easily. So that's what I did here. The angle of s plus 1 is the angle of minus 2 plus 4j, which is tan inverse minus 4 over 2, which is 116. This angle from here to here is minus, sorry, plus, because we said counterclockwise is positive. So this one is plus 116.6. And I will do the same with the other what you call terms. So I will do the same with s and s plus 2. So if I do it that way, For s plus 1, we said it will be the square root of 20, and the angle is 116. That's what we did just now. So we got that one, 20 the amplitude, and the angle is 160. For the other one, for s, I'll put minus 3 plus 4j. The amplitude will be the square root of 9 plus 16, which is the square root of 25, which is 5. The square root of 25. Now, the square root of 9, 3 squared, plus 16, 4 squared. It will be 5. And the angle is 126 in the same way. I can calculate it as tan inverse 4 over 3. So I'll get it as 126.9. And I'll do the same with s plus 2. So I'll put minus 3 plus 4j there. It will be minus 1 plus 4j. So the amplitude will be 1 squared plus 1 squared, because it will be plus 2. So this will be minus 1 plus 4j. So 1 squared plus 4 squared plus 16, the square root of 17, the amplitude. And the angle is 104. So I know all the amplitudes and all the angles. Now I can get the amplitude of f of s using the values that I've just got. So it will be the amplitude of 20 and square root of 20 over 5 divided by 17. That's the amplitude. If you remember from here, let me go back. This is the f of s that I want to know. So to be able to do it, be able to do that, so for the amplitudes of the zeros divided by the amplitudes of the poles. And for the angles of the zero minus the angle of the poles. So that's what I have to do in order to get the amplitude of f of s and the theta of f of s. So if we do that, if you go back now to the to what we have here, we got all the amplitudes and all the angles. Now we just have to get the overall. So the amplitude of the zeros, which is the square root of 20, divided by the amplitude of the two poles, 5 and 17. The square root of 17 and 5. So this gives me 0.217. That's the amplitude of my f of s. For the angles, it is 116, the angle of the zero, minus the angle of the first pole, minus the angle of the second pole, which is minus 114.3. So now I know what is the amplitude of this one, okay, of f of s at this point, when s is minus 3 plus 4j. The amplitude is 0.217, and the angle is minus 114.3. So the f of s for that particular s will be a vector from 0, which with a length of 0.217 and direction minus 114.3. So just to evaluate f of s using s as a vector. So now let's go back to our objective. Our objective is to solve for this. We want to find a solution for this one equal to 0. Okay. We know now how to represent s as a vector. And we know how to evaluate t of s, or the denominator, as a vector. If we have s as a vector, how to determine this, how to calculate it for a different value of s. So this is the equation that I need to solve. Or just writing it in a different way, I can say that this one equals to minus 1 if I move 1 to the other side. So k g of s naught, h of s naught equals minus 1. What does it mean in terms of the vector? Now, vector notation. It means that the angle of this one, when you have it this way, let me just draw it here very quickly. I'll draw a vector in this direction. This is minus 1. What is this angle here? What is that angle? If you measure it from this point to that point, what will it be? Is it 90 or 180?
180.
180.
180. So kgs h of s equals minus 1. It means the angle of this one should be the angle of this minus 1. And the angle of minus 1 is 180. So I can say that KGS H of S have an angle of 2K plus 180 times 180, which means an odd multiples of 180, because it could be 180, it could be 3 times 180, it could be 5 times 180, it could be 7 times 180, but not 360, not 2 times 180, not 4 times 180, because otherwise it will be a vector in this direction. So a vector in that direction, it will be 180, or you go another 180 plus another 180. So this means 3 180 and so on. So a multiple, odd multiples of 180, that direction. And the amplitude of this one should be the amplitude of 1, which is 1. So the solution of this one, the solution of this equation, will have angle equals to odd multiples of 180 and an amplitude of 1. So any solution have to satisfy those two conditions: the angle condition, the direction, and the amplitude. Amplitude is 1, and the angle should be 180 or 3 times 180 and so on. So we'll have that the amplitude is 1 and the angle should be odd multiples of 180. So that's something that will help us to draw later on the root locus. So a value S naught, which is a solution, which is a pole of the closed loop transfer function for any value of K, have to satisfy this condition that the angle should be odd multiples of 180, and the gain should satisfy this equation. It should give me a magnitude of 1, or amplitude of 1. So K is 1 over G S naught H of S naught. So those are the two conditions for any point to be on the root locus. Let's say we have this equation, okay, this open loop transfer function, and I want to check whether S equals minus 9.47 is a pole of the closed loop transfer function, which means it is on the root locus or not. And what is the value of K that will make this one a solution of this one? So I need just to check here to see whether this is a solution. So what will I do? It has to satisfy two conditions: the angle condition, 180 or odd multiple of 180, and the magnitude condition, it has to be 1 for it to be on the root locus. So let's check the angle. The angle of this one, I'll put S equals minus 9.47 here. So I will have it as remove K. So the angle without the K, remove the K. So 1 over S plus 10, and S is minus 9.47. So what will be the angle? The angle of this one, what is the angle of 1? This is 1 from here to here. What is the angle?
0.
0. So this is 0. What about S, which is minus 9.47? So minus 9.47 will be this number, this vector, from 0 to minus 9.47. So this angle,
180.
which is 180. And then we have S plus 10. S is negative 9.47, and plus 10 will give me a positive number. So it will be another vector in this direction, which will be again another 0. So the solution will be 180 in this case. 0 minus 180 minus 0, it will be minus 180. Minus 180 and plus 180 is the same. This is plus 180. This is minus 180. It's the same thing. So it is 180, which means this point is a pole of the closed loop transfer function. Because remember that we have this condition, two conditions. To be a pole, to be a solution of this equation, either the angle should be 180 or odd multiple of 180, and the other condition, you have to choose K that will make the amplitude of this one equals to 1. So those are the two conditions. So the point minus 9.47, satisfy the angle condition, which means this point is on the root locus. It satisfies the condition of the angle. Now I have to choose K such that K equals 1 over GS H of S when S is 9.47. So I'll just substitute 1 divided by S. Remember, S is 9.47. S plus 10, 10 minus 9.47. If you try to get the amplitude of this, you'll get it as 1 over 5. because it will be 1 divided by S is 9.47. المثال اللي معي هنا بسيط لأن معي vector which is on the real axis, so I don't have complex numbers, so it's easy to get the amplitude. The amplitude of this one is 9.47 times 10 minus 9.47. ما أدري كم الرقم هنا بيكون. 10 minus 9.47. It will be
0.53.
0.53. If you try to calculate this, you'll get it as 1 over 5. I mean, this will be 5. 0.53 times 9.47 is 5. So the amplitude is 1 over this, which means 1 over 5. I mean, the amplitude, which means the amplitude on the value of k in that case, not the amplitude of the transfer function or the closed loop transfer function. So this value of k will put this point on the root locus. Because you have to satisfy both conditions. So the first condition is from S. I made sure that this S, 9.47 minus 9.47, will make the angle minus 180. And the value of k at that point is 1 over 5. So the condition is satisfied by choosing k to be 1 over 5 to satisfy both conditions. So the solution for this one in the S domain, the solution of this one have to satisfy two conditions. The angle condition, it should be, I mean, it's the same thing as what we did say now. The angle of G of S is I mean, if we write this one as G of S equals to minus 1 over K, then the angle of this have to be equal to the angle of that. That's one way of saying it. Or you can say the angle of this should be minus 180. It's the same statement said in a different way. You got it? This is an equation, this one, an equation. So for this to be equal to this vector to be equal to that vector, the angle of this one, KGS, should be equal to the angle of minus 1, which is 180, or odd multiple of 180. Or you can say it another way, this angle should be the same as this angle. It's the same thing. The angle of G of S should be equal to the angle of minus 1 over K. So it's the same thing. Or G of S equals to 180, because this is still a number, okay? A number which is just a real number, minus 1 over K. Okay, so the angle of G of S is odd multiples of 180. So that's one condition. So the root locus is the set of points in the S plane where G of S phase equals to 180. So this is one condition. The magnitude of G of S should be equal to the magnitude of G of S should be equal to the magnitude of 1 over K. Or K equals to the amplitude of 1 over G of S. Just another way of saying it. This could be written in a different way in this fashion. G of S is N numerator over denominator. Okay. So just another way of writing this in terms of the numerator and the denominator. Now this will give me one thing. When K equals 0, what will happen? For this to be equal to 0, what will happen to this one or this one? When K is 0, what will happen? If this is 0, what will happen here? خلنا نعملها بطريقة أو أسألكم بطريقة أخرى مختلفة. لما K ب0 وش اللي يحصل هنا؟ علشان K تكون 0 وش اللي بيصير هنا؟ الS وش بتكون قيمة الS اللي تخلي K 0؟ S بتكون وش؟ بتساوي أيوة مهند
minus B.
minus B. The poles. So the poles of the open loop transfer function are the solutions when K is 0. When K is 0, your solution is the poles of the open loop transfer function. Okay, the solution of the characteristic equation of this equation, the solution of this equation here that we have here, the solution of this equation are the poles of the open loop transfer function. the poles of G of S. Okay, when K is 0. Or what else? From here, not from here now, from this one here. What will make K 0?
ES must equal to 0.
D of S equal to 0. So that's another way of saying it, because this one will be in the numerator here. So just another way of seeing it from this expression of G of S. Okay. What about K equals infinity? When K equals infinity, for this to be equals to infinity, what should be the case for this to be infinity?
In S should equal to 0.
The
Or S
NS
equal to...
True. NS equals to 0, which means your S should be equals to ZI. You should go to the zeros of the open loop transfer function. So for at K infinity, your S will go to the zeros of the open loop transfer function, which makes N of S 0. Or your D of S is infinity, because this will come up here. Your D of S is infinity. And D of S will be infinity when S is infinity. So that's why if you don't have enough zeros, your S, the solution, will start from the poles. It will go to the zeros, the solution as K changes from 0 to infinity, or to infinity. So when K is infinity. So that's why we had that results before. You start from the poles of from 0 and -1, from 0 and -1. And then if you don't have zeros here, you'll go to infinity. Okay. Now let's just check one thing here. If we check at a point here, let's take a point just to check whether this point here, is on the root locus or not. This point is minus 0.5, S equal minus 0.5, and this one here is 1 plus 1J. Is this point on the what you call root locus or not? It has to satisfy two conditions: angle condition and magnitude condition. So the angle condition, this angle here, the angle for this one will be the angle of the zeros minus the angles of the poles. So we have this vector from 0, and we have from -1, from this one here, this vector. This vector here. Sorry for that. It seems I'll have to keep it. Okay. Sorry for this. I'll have to erase it now, so I'll just have to continue. So I'm just checking the what you call the angle condition and the magnitude condition. The angle condition, this angle here is I mean, if you try to get the angle of this one and the angle of this one, you can add them up, it will be 180. Why is that? This angle here is 1 plus this angle, but this angle is the same as this angle. So it means this one plus this one will be 180. It should be 180 without measuring it. I mean, you can measure it using the tan inverse and so on. But from seeing the graph here, I can say that it is 180. Okay, so that angle here is 180. 180. So the angle is satisfied. Now for the amplitude, I want the amplitude of this one to be 1 over K, which means I want K to be the amplitude of 1 over GS. So I'll just substitute with S equals minus 0.5 plus 1J, 0.5 squared plus 1 squared, multiplied by S plus 1. So it will be again 0.5 squared plus 1 squared. It will be 1.5. So if I choose K equals 1.25, this point here will be on the root locus with this value of K. It starts with K equals 0, the graph, and then it will end up at this point when K equals 1.25. Your solution will be here at K equals 1.25 for that example. So just an example here of the root locus of a simple function. So to check again, to check whether your point is on the root locus, you need to satisfy two conditions: the angle condition, and then find k that will give you the needed amplitude. That will make you choose k such that the amplitude is 1 over g of s. So those are the two conditions to be on the root locus. We can draw it again using MATLAB. So you can just take your transfer function, open loop transfer function, put it in MATLAB, and it will draw the root locus using rlocus command. That's in MATLAB. In CLab, you have to write it in this way. You put s, you define s as a variable, and then you define your numerator, s plus 4, and your denominator, s plus 1, s plus 2, s plus 6. And then you define your system, transfer function, numerator over denominator, and use the command Evans. Evans is one of the people who worked on root locus. So instead of rlocus in MATLAB, in CLab, you use Evans. And then you define your transfer function. And this one is just to sort of define your what you call the space where you want the drawing to happen. But Evans is the command that you will use in CLab. Okay? And in MATLAB it is rlocus. So those are there for you later on if you want to use them to draw the root locus using MATLAB or ScienceLab or CLab. Now we want to draw the root locus. So again, we've seen some properties. Now we want to start drawing the root locus, but I think I will stop it here and we'll come back to this next time. We'll see what are the properties that we want to make use of, and then how to use those properties in order to draw the root locus of the system. I will stop it there because otherwise I'll confuse you. And then on Wednesday, inshallah, we'll learn how to draw the root locus, and we'll look at some of the properties that we can make use of in order to draw the root locus. We've just started, so don't worry if it is not clear enough. So today you know that the root locus is the solution of the characteristic equation, the values of s as k changes from 0 to infinity. What are the values of s that will make 1 plus k gs h of s equals 0? How we can find it? You can draw it using the MATLAB, or you can draw it using ScienceLab. So for us, now we are lucky, we can just draw it using the software. We just have to know what is the open loop transfer function, put it in MATLAB in one command, and you'll get the root locus. For people who worked on control engineering and design of controllers in the 60s and 50s, and maybe even in the 70s, it was not that easy. They cannot just put it in MATLAB or ScienceLab and they will get the sketch of the root locus. They did have to solve the equation 1 plus k gs h of s equals 0, which is a polynomial, a very complicated polynomial. They have to solve it for different values of k in order to sketch it. So there are people who are mathematicians, our control scientists, our control engineers. They said why we have to do it that way, why you have to solve this equation for different values of k. Let's sketch it. And from the sketch, we can understand the system and then design our controllers. So they came up with this root locus sketching procedure, which I will introduce next time. How to draw the root locus, the solution, without solving the equation. That's the objective. How to draw, sketch the root locus, the position of your s, which will give you the solution of the characteristic equation for different values of k without solving the equation. So we'll learn that procedure next time. It's not that difficult. You just follow a certain procedure, which is not that complicated. You'll be able to sketch it. But again, we have now MATLAB. We can do it. We can check our answers whether they are correct or not. Later on, after 2 weeks, we'll learn how to choose k in order to put our pole, our closed loop pole, in our desired position. We want S to be in a particular place, because if my S, my closed loop transfer function, have S at that position, my zeta will be something, my omega n will be something. So after 2 weeks, we'll learn how to tune our K, how to change it in order to put S in a particular place. Like in this week and next week, we'll just learn where S will be when I change K. So just to understand what happens when you change K, what happens when you introduce a new zero, what happens when you introduce a new pole.